Welcome everyone to Flower Monthly for July. It's great to see everyone here. And I'm happy to announce our agenda for today is super exciting. We'll have our usual welcome. I'll run through the agenda. We have a couple of important flower updates that you might be interested in. And then we're going to jump into two fantastic invited talks. And you can see both the invited speakers in the room already. We have Daniel Jimenez. He is a PhD student at La Sapienza, University of Rome. And he is going to be telling us about his work to create a tool that it can be extremely useful, we believe, for people doing federated learning, both research, productization, or proof of concepts that tackle this thorny issue of non-IAD data and how do you handle that type of situation. After his talk, and we take a few questions, we're then going to jump into another fascinating piece of research. This is a system called Retox. I might have said that wrong, but we can always maybe get a fix later on when we get the talk. But essentially one of the early methods that allow us to do scalable neural network training over distributed graphs. And so most of the federated learning methods you would have seen out there are looking at more sort of conventional model architectures, but there's a important category of models out there called GNNs and distributed graphs of various kinds that Ashish Kaluri from the National University of Singapore has been tackling in his research. So with that, by way of an agenda for July, let's look at the flower updates. There are just two flower updates I wanted to provide. And let me just see, one of them involves Javier that is not quite joined yet. But anyway, the first update is that you would have remember the Flower Summit about a month ago on YouTube. This event took place over 2 days. We had a variety of people from industry and academia speaking. We also provided some important announcements for the framework. We also gave a roadmap of where we think things are going to go. There were some tutorials there as well. Well, if you weren't able to come physically to the event, and if you weren't able to join the YouTube stream that was available at the time, what we've done is we've packaged up all the talks and put them on YouTube for you to sort of watch at your own leisure. So you can go to our YouTube channel that uses the Flower Labs signifier that you can see here, and you can see all of those talks right now. So that's been posted there if you're interested. And the other update that I wanted to share with you is also really important. And that is one of the key announcements at the Flower Summit was a program that we're calling the Summer of Reproducibility. And this whole initiative is moving towards working more with the community to create a series of baseline implementations of key methods of federated learning. And what we're doing in the Summer of Reproducibility is coming up with a 3-month sprint where we work with the community to come up with a series of implementations of key papers out there. And then we've put up $100,000 US to help reward those who are willing to put in the time to carefully reproduce existing algorithms. And then so each individual successful implementation that we can accommodate into Flower and enable and expose for the other users to utilize are going to be given a $2,000 award. And we've already made two of these awards already. I'm just going to introduce Javier, who's going to say a bit more about this. But essentially, we're going to launch this program this week, and Javier is the key organizer of this program. And so over to Javier, if you would like to say a few things about this really important step forward for the federated learning community.
Yes, absolutely. So as Nick mentioned, the idea of the Summer of Reproducibility is to join efforts as a community. It will be a 3-month sprint in which we have carefully selected 50 baselines that we consider are good foundations for the future research of federated learning. So in this list of 50 baselines are popular papers that are out there already accepted in peer review venues. And the idea would be that once we launch it, which will happen very likely tomorrow, you will see a dashboard in GitHub, and you can go through all the baselines, pick a baseline you might find interesting, maybe because it's very close to your research topic, and then you will click on it, and then you will start the process of contributing to this, which the first stage will involve in telling us what experiments in the paper you are particularly interested in contributing. And then the process is fully guided. We'll be releasing the instructions step by step. So I'm sure everyone will have a great time contributing. And yeah, we'll be interacting with you along the process. So it should be fairly fun.
Yeah, I think this is super exciting. I think when I think of this program, an important dimension to it, I think, is the fact that we're going to strive to enable exposing these implementations with a common API. So it's very, the way things happen now in the best case is that you have to look at someone's repo, maybe they've open sourced the code, but for everything you want to compare against, you need to study how did they implement, you really need to understand it to really get the most out of that algorithm. And so we think an important step forward not only is to have implementations out there, but have implementations that are normalized and structured in a way that somebody doesn't need to know the nuts and bolts of how they function for them to compare or even use. And so this is going to be a key dimension that the community is really missing. What you're seeing here is a visualization of the website that will be explaining everything for you. We also have GitHub sort of workflows. You can sort of look through the GitHub to see how it's going to work, all launching this week. We're also very happy to have Ask Anything sessions whereby you can drop in, ask us some questions and so on as a way to bootstrap this effort. That's somebody I was talking to Javier just earlier. So very excited to see this thing take off. Now let's move on to our two invited speakers. Our first invited talk for today is given by Daniel Jimenez. As I mentioned earlier, he is at the La Sapienza University of Rome, so a very prestigious university in Italy, where he's a PhD student working towards a system called FedArtML. So it's a great name. It's a tool for allowing people to explore and experiment and make progress on this thorny issue of non-IAD-ness within federated learning. And so, Daniel, thank you so much for joining us today. We're really excited to learn more about your research.
Thank you very much. Thank you very much for the introduction. And yeah, I'm also really happy to share this with you all. So now let me share my screen.
We can see it fine. Thank you.
Okay, great. So, hello everyone. As you say, my name is Daniel Jimenez, and I want to introduce you FedArtML, which is a tool for creating datasets for federated learning research. Currently, I am in my first year of the PhD in data science at Sapienza, as he mentioned. And so let's get started. So, okay, first of all, I expect you all are familiar with Avengers. And of course, I hope you know who Tony Stark is. If not, that is pointless, but still, I wish you know it. And I remember that some time ago, I was asked about what was Tony Stark's greatest invention. And so I thought about some of his inventions that came to my mind. And for example, I remember that he, for example, constructed the Hulkbuster, the Edit glasses, the art reactor, the Iron Man armor. Those are pretty good inventions he had. But when I was thinking deeper, I realized that the greatest invention of Tony was indeed Jarvis, his AI tool that he used for like an assistant. And indeed, that tool permitted him to actually create plenty of smart astounding inventions. So it is the most important job he did. And thinking about it, at the very beginning of my PhD, with our research group, we were thinking like we should create first our own Jarvis and our own tool that permits us to do federated learning research in a fast and controlled way. So from there is what born federated learning for artificial intelligence and machine learning, aka FedRML. So that's a tool that enables the creation of federated datasets starting from a centralized one, where we can control the level of heterogeneity of the data distribution. That is a concept that is usually called non-IIDness, that you can find it into the literature. So that's how, after reading some bibliography, we realized that there is still a need for benchmarking algorithms that tackle the non-IIDness, but doing it in a controlled manner, in a systematic way. And moreover, to achieve our goals, it is mandatory to have metrics that permit us to quantify the degree of heterogeneity of the datasets. And besides, for traditional research, we usually have plenty of centralized datasets, but when doing research in federated learning, the availability of such data is much more limited. So among our main contributions here, I can highlight that we provide the researchers with metrics that will permit them to quantify what is the level of skewness in the datasets in a federated fashion. And second, we provide a library that permits to obtain federated datasets starting from that centralized one. And basically here, we can take almost any kind of dataset and split it into federated clients. And of course, the main idea is to control the degree of non-IIDness that we want over that created or simulated dataset. And of course, we run some experiments using well-known centralized data to be able to give a shape of what our tool works like. Okay, so let's now go a bit deeper into a formal definition of what we mean by a centralized dataset. So as you can see, as a dataset is defined as a collection of features and labels that in this case are represented by X and Y. And when talking about federated datasets, what we mean is dividing those datasets, that dataset into different multiple disjoint clients. That's what we intend to do with this. And when we define the distribution over labels for each client, and the sum of the distribution of the responsive variable. This is pretty much what we mean about the distribution over those labels. And similarly, we define the distribution over the L feature space of each client and the sum of those distribution over the features. So this is basically those definitions when we talk about the distribution of labels and features. Okay, so when talking about non-IID data, there is a high-level classification for different types of skewness. So starting with the part of identically distributed part, we have in the first place the label skew, which is one of those that happen when the distribution of the labels differs among the clients. Second, we have the feature skew, that is the one that happens when the distribution of those features varies from one client to another client. And thirdly, we have the quantity skew, which is about a significant difference in the number of samples in each one of those clients. And now going a bit on the independence concept, what we have is the temporal skewness that occurs when the distribution of the clients depends on time, or even we can see that depends on the space among those clients that we have already created or that we can find in this federated fashion. Okay, so one of the innovations we introduce is the capacity to quantify the degree of non-IIDness. This is something relevant that we think it is pretty useful. And of course, I remember from the last summit, this is a hot topic that was given there like an open question or open problem to work with. And so far, we have only focused on resolving the label skew problem. And we propose in the first place the Jensen-Shannon distance, which is a metric used to measure distances among distributions. So we consider this distance since it is between 0 and 1, And of course, it is interpreted that when the distance is close to 0, then the label distribution is IID. And of course, when it is close to 1, then the label distribution is non-IID. Moreover, it is asymmetric, and of course, it satisfies the triangular inequality, which are useful properties that we want for a metric of this type. And if we want to take the distance of more than 2 distributions, we only have to take the mean of all those pairwise distances. We also introduced the Hellinger distance to measure the non-IIDness of the label distribution. And it has the same properties as the Jensen-Shannon distance. And also, if we want to take the distance of more than 2 distributions, what we have to do is only to take the mean of those pairwise distances. Now, our second innovation here is the implementation of methods to divide the centralized data into multiple clients, and again, in a controlled and systematic way. So our first implemented approach is the Dirichlet-based method, where we first have to define a value for alpha, that it is related to the Dirichlet distribution. And that value will control the skewness of the data that we are generating. So that means that the smaller the value of alpha, the more non-IID data will tend to be. And once we have defined that alpha, what we have to do is next to draw samples from that Dirichlet distribution. And in that way, we can obtain the distributions that each one of the clients will have. As I told you, we are working here so far only with the label distribution. Good. Now, our second approach to divide the data is the percentage of non-IIDness based method. It's a bit large name. And in this approach, we define a percentage of non-IID data, which will control that skewness of the data. And that means that the higher the percentage, the more non-IID the data we want to generate will be. And then we select that proposed percentage from the data, and we distribute the labels evenly across the clients. And finally, we take the remaining part of that data and distribute it randomly across the clients. Okay, so our library is already available in PyPy, and it is compatible with Python versions about 3.5. Moreover, we added the respective documentation for everybody to be able to understand the classes and all the functions that we are using. And of course, it is on GitHub. And even we provide some getting started examples for the tool to be tested easily. I think that is a way for everybody to easily connect something and run the notebook or run the code that is there. And in that way, it is easy to check what is happening with this tool. And of course, last but not least, the outputs of the library are compatible with Flower, since mainly the outputs are composed by dictionaries and lists. So it is already fully usable if you are working with Flower. Okay, now I want to share some of the use cases that we want to showcase here, because I want you to understand how our tool works and what it is useful for. So one nice thing that the tool includes is that it can generate interactive graphs to check the distribution of the labels. So for this example, we employed the Cypher10 dataset, which contains images of more or less 10 classes, let's say. And as you can see here in this picture, in this blue part, there are 2 sliders that will permit to control or to simulate the behavior of the distributions in real time. And if we change the alpha or the local nodes, we can see how the distribution will change automatically. In this case, the alpha was defined as 0.01, and we employed 4 local nodes. Just an example we wanted to show. And from this plot, we can see how the distribution of the labels is completely different among the clients, which leads to a Hellinger distance, the one that we introduced before. That is basically 0.98, which means that the distribution is really different. And inside the same use case, we employed FedRML together with Flower, and we wanted to train a centralized and a federated learning model. So we wanted to compare them, and we employed different values for alpha, ranging from 0.01 to 1000. And we managed to get this plot that I am showing right now here, where in the x-axis, you can see the Hellinger distance, which is the metric that measures the degree of non-IIDness of the labels. And in the y-axis, you can see the F1 score. And then what we did was comparing the centralized learning with the federated learning approach using federated average, and fedprox. So we wanted to compare how different it might be. And as expected, the higher the degree of the non-IID, the poorer the model performance. So you can see here, it goes decreasing. And also, fedprox improves a bit the model performance when the label skew is higher. As a second use case, we use the FissionNet 2020 data that is centrally data for electrocardiogram arrhythmia detection. So with our tool and the percentage of non-IIDness method, we federated the data into 6 different clients. So in this case, we use the percentage of non-IIDness, and it became something like 60%, which is translated to a Jensen-Shannon distance of 0.66. And each one of the plots showcases how the distribution of the labels differs among the clients, as you can see over here. And you can see how some of the clients have more arrhythmias for one class, while in others, there are not that many arrhythmias. And again, combining federated RML and Flower, we compare the performance of decentralized and federated models. So we increase the degree of the label skew and the number of clients. Of course, we did this, for example, that to show here that the more the non-IIDness, the worse the performance is, and also increasing the number of local nodes will generate a poorer performance. So after showing these use cases, the takeaway message I want you to have is that we implemented various simulations in a simple manner, always controlling the degree of heterogeneity of the labels and even quantifying the non-IIDness of the label distributions. And that's all possible with our tool. That's the aim of our tool. So let me give you some of our initial conclusions so far. So the Jensen-Shannon and Hellinger distances are appropriate to quantify the degree of non-IIDness of the label distribution among the clients. And second, our FedRML library managed to reproduce federated datasets starting from a centralized data, facilitating the comparison of centralized and federated learning. And thus, as a consequence, the datasets are consistent and generated with measurable levels of heterogeneity. And of course, to have a proficient version of our Jarvis, we still have a long path to follow because we plan to expand our tool, including methods to measure and simulate scenarios with feature skew, quantity skew, temporal skew. And moreover, we plan to use our tool to conduct a systematic and controlled comparison of aggregation methods such as FedPro, FedYogi, FedAdam, and all those methods that are implemented already in Flower. And you can find here some of the references we employed while doing this. And that's it. It was a fast journey over our tool that we expect will be helpful for the future research path, and we will continue on this path. And it was a pleasure to share the advancements and all the things we have done so far. And I invite you all to install it and, of course, play with it and let me know what you think, if you think it's useful or not. That would be really helpful. So this is it. This is my presentation. I don't know if there are any questions so far.
First of all, thank you so much for the presentation. It was really great work. Really great. I really enjoyed a couple of those slides too. The Tony Stark slide at the start is a nice touch, and also the slide at the end with the quote. I haven't seen that done before, which is really cool touch.
Okay.
I have a couple of questions I can pull from the different places we get questions from, like Slack and so forth. Yeah, one question is asking, okay, so basically the question is saying, with this tool that you've made, have you kind of made any sort of empirical observations that you thought that were interesting to you, that were new? It seems like you're able to really play with the granularity of IIDness in a very interesting way. So through this tool, what have you kind of discovered that you didn't expect to see?
Yeah, and indeed, that is what we wanted to do, because so far what we have seen in the literature is that there is research and there are non-ID scenarios generated, but the way to control it was not there. Although you can control, for example, with the alpha of the digital distribution, properly controlling and measuring it, it is not really there. So I don't know, for example, you generate a distribution with alpha equal to 0.5, but you don't know if 0.5 is much or is not much regarding the non-IIDness. So that is one of the things to do. And yeah, indeed, it will help us to be able to really understand how the non-IIDness and up to what point the non-identity will harm our models. I don't know, for example, a conclusion is that we are expecting to do is that after 50% of non-IIDness, the models start to really decrease. Before that, they do not suffer that much. So that's one of the huge conclusions we expect to have from there.
Interesting. Cool. I think that really answers the question they were asking.
Okay.
I see. Javier had a question. So I mean, rather than read it out, I'll let him speak.
Yeah. Okay. Well, first of all, thank you for the talk. Very interesting. So I'm familiar with how to partition data with following the Dirichlet distribution, right? With alpha, everything is quite convenient. But I think after listening to your talk, I was wondering if, for example, with your tool, you could also control not only the distribution over the labels, but for example, what about if I want to control how many training examples each client has, because that's a different way of heterogeneity, right, in the data. If that's supported or if it could be supported easily, that's one question. And the other question is, do you think that by controlling this with a single scalar is enough to do? Is enough? Like, for example, what if I want to have, for example, something more similar to these pathological data distributions where I say, just 4 classes in this class, in this client. Yeah. Do you have any thoughts about that, or maybe future plans?
Okay, so regarding your second question, I will start from that. Also, for the first one, it is not yet implemented, but what you are mentioning is basically the quantity skew problem that we have. So indeed, that will be our next step after doing the feature skew. And indeed, it is supposed to be generated because that's something we want to do. And we want to cover the 4 parts, which are label skew, feature skew, quantity skew, and temporal skew. So that's what we want to try and do. And yeah, we already have ways to do it, but what we don't have is our hands to do it. So that's the reason we haven't finished that. And regarding the second question, before you ask, I think it is enough. Now that you ask, I think that maybe it would be useful to have more parameters. Even thinking, for example, that one thing that comes to my mind is that you can have, you can control the non-IIDness of the labels. But what if also I want to control the non-IIDness of the features? But what if I want to control the non-IIDness of the quantity, the 3 of them at the same time? Maybe that could be really interesting to understand, and thinking that if I have the worst case scenario, the pathological scenarios that we can measure already and we can generate them, it will really harm. I mean, we expect it to harm a lot the model, but we want to check it. So yeah, indeed, I think even using more parameters would be interesting. Of course, it will generate a more complex approach, but yeah, it would be great to have.
Okay, yeah, great. Yeah. Sounds looking forward to get all those features.
Good.
One more question I see come in, which is, once you've solved the non-IDness problem, what's the next thing you want to tackle? I guess they're saying, given what you've seen so far in the FL space with this tool, what do you see coming down the pipe for you after this tool?
After doing this tool?
Yeah.
Okay, so indeed, what is coming, at least for what we have done so far, the first thing to do is that we want to do a benchmarking of different algorithms. Why? Because right now, and we have been following some papers, there are benchmarks, but they are selected ad hoc. They are not really systematically selected. So that is the first thing we want to do. And the second thing I want to work with together with this is to generate a new baseline, a new algorithm, or a new aggregation, something similar that will tackle this non-IIDness. And when I create that solution, I will implement with this tool all the possible scenarios that can harm the models. And in the end, what I will be able to say is, this new tool that I have, this new aggregation or this new method or this new personalized federated learning works, and it works to this extent when the data is following this non-IIDness in the label, the features, the quantity, all that. That's what I think it follows.
I see. Great. That was a pretty good answer, because you had quite a complete answer to that kind of question that was posed to us. Okay, great. Well, thank you so much for coming today and sharing this. And even more importantly, thank you for deciding keep it open source and allowing other people to build on top of it. So it's a really great contribution on that front.
For sure,
Excellent.
that's important. Yeah, that's so important for us.
Great. Well, let me move on to the next part of this month's Flower Monthly. It is going to be another talk, another invited talk from Ashish Choudhury. He is based right now in the National University of Singapore, but I do believe he happens to be in Cambridge, of all places, right now on an internship with Bell Labs. So it's great to have you here today, and great to see that you're physically close to where I am, and we can meet up later on. So thank you so much for joining us today and sharing your work. Let me first ask. So how do you pronounce the system name? Is it Retiox, or I don't know how you would say it?
It's it's called Retexonic.
Retexo.
Yeah.
Okay, it's a really cool name. Okay, so then your work is all about how do you train neural networks over these distributed graphs and so on.
This work is about that. My thesis is also on this, but also doing it more privately, like including things like differential privacy and stuff.
Fantastic. Well, this seems to be right up our alley. So I'm going to stop sharing and allow you to take over and tell us all about it. I remember I met you last time. Last time I saw you physically was at the Flower Summit.
Oh yeah. I attended the summit. It was great. It was a great experience.
Okay, amazing.
I mean, meeting all of you guys, working. We all have similar interests, so it was nice to meet a lot of people who I was able to talk to with similar interests. People could understand my work and then give me feedback. It was pretty good.
Oh yeah, there's definitely a huge value in having like a concentrated community that always shares a common vision. So yeah, cool. I'm really excited to see your work.
Can you see this?
Yep, looks good.
Hello everyone, I'm Ashish, and thank you for the introduction, Nick. It was a great introduction. So I don't have too much to say apart from, I'm a PhD student currently with NUS, in NUS. I'm a final year PhD student. Today I'm going to talk about how to efficiently train neural networks over distributed graphs. So a brief introduction to my research trajectory. So I've worked in the past on many things. I've worked on blockchains, and my work in blockchains has been pretty popular in the past. It has created some news as well. I had a lot of fun working on blockchains. And then I worked on program debugging and synthesis, and I had several good works in that. And I also won like a best paper award, like my work won best paper award at one of these conferences. And my whole thesis work is on trustworthy federated learning. It's not on the previous topics. And this, I'm looking to design like federated learning algorithms for graphs, heavily distributed graphs. And I also want to keep them trustworthy, which means like having nice things like privacy and robustness. So today I'm going to talk about one of those works. So before going deep into the work, I just want to give you a flash of like how was Flower useful for this work. So typically when you want to train a graph neural network on a graph, so you do it in the centralized setup. So let's say there's an attributed graph, you train a graph neural network, and then you learn representations for each node in the graph. But let's say you distribute the graph, especially you fully distribute the graph where each client holds just a single node. So here a client is a mobile device, and then you have, if there are n nodes in a graph, you have n devices, and then they communicate with each other, right? So if you have such a graph, then if you want to train a neural network, a graph neural network in a federated learning fashion, then it's basically impractical. I'll show you why, but it's impractical. So you can't train a GNN. So what we do is we introduce our work Retexo, which creates a different version of graph neural network called Retexo GNN. And Retexo GNNs, which are implemented on Flower, on top of Flower. So Retexo plus Flower, we create Retexo GNNs, which are practical to train in the federated setup. And that means we can do the applications, we can basically implement the applications, we can satisfy the applications for which graph neural networks are used. So it looks like this. So there's a Flower server, and then there are Flower clients. So the beauty of federated learning over distributed graphs is that you have two kinds of communication channels. There's client to server communication channel, and then there's a client to client communication channel. Unlike other federated, like typical federated learning setups, there's only client to server federated learning, client to server communication channels. So Flower provides client to server communication channels, but in order to do this federated learning over graphs, we also create client to client communication channels. We extend Flower to have this as well, this functionality as well. So yeah, eventually by adding a little bit of functionality to Flower framework, we are able to train the first GNNs for fully distributed graphs. Okay, so let's go to the details of the work. So machine learning over graphs is very important for many applications. For instance, social network analysis, recommender systems, anomaly detection, and the list could just go on. And graph neural networks are state of the art in this field. They have been already implemented and deployed in production at several companies. So the graph neural networks are layered architectures where you have many aggregation layers and classification layers, and they're interspersed with graph adjacency matrices. This all looks very complicated, but let's simplify this. So typically graph neural networks are used to find representations of nodes. So let's say here we want to find the representation of node A. So the way this happens is that, so let's say you have a graph neural network with two aggregation layers, AGG1 and AGG2. So to find the representation for A asks its neighbors to give their representations, intermediate representations, coming from aggregation layer 1. So here in this graph, A's neighbors are C and D and B. So it just asks them for intermediate representations. And then because C and D and B need representations from their neighbors to pass through aggregation layer 1, they ask their neighbors, okay, give me your features. And then once they get the representations from their neighbors, they pass it through aggregation layer 1, and then they have intermediate representations which they give it to node A, which can be passed through aggregation layer 2 to get the final representation. So basically this is GNNs propagate the representations over the edges of the graph, and this is called message propagation or feature propagation. So this way you can aggregate information over the graph. So there are two kinds of setups, essentially, one a centralized and two a distributed setup. So in the centralized setup, you have the graph over, so in the centralized setup, you have the node features and the edges in the same place, and GNNs have been designed for this setup. So in this case, the message propagation happens locally, whereas in the distributed setup, there are clients, and each client stores a subgraph or a partition of the graph, and then there's a server which doesn't know the graph. So the clients basically do not want to or do not share the graph with each other. So in this setup, you need some sort of collaborative learning or federated learning procedure to learn a GNN. And as I said, learning a GNN would require message propagation, but in this case, the message propagation would require communication among the clients because there'll be inter-client edges. So why do we care about distributed graphs? Distributed graphs are everywhere. So for instance, you might have at an organization level, geopolitically restricted social networks or financial networks, where like you have a part of the graph in some country and you cannot share that data with some other country. Or at an individual level, you can have like a network of personal devices or sensors. So think of it as like a contact tracing kind of an application, which the governments have done in the past few years. So like you have a huge network of connected individuals and they're meeting each other, and they carry their mobile phones everywhere, and the edges are formed from proximity channels. And the applications there are like classifying the users based on that, based on the features that they store on their phones and the people they meet. So just to summarize federated learning in this regime, so you have like a centralized setup where essentially there's no federated learning. The graph is there in the centralized servers, and then you train a GNN. And then you have a cross-siloed setup where there are a few clients storing massive subgraphs, and you conduct federated learning. Here there's client-to-client communication, but at a smaller scale, only for inter-client edges. And then you have a cross-device setting where like you take it to the extreme, and there's the devices are the clients, users' personal devices are the clients, and each client holds information about just one user or one node of the graph. So there's a fully distributed setup. So in this case, if you want to do federated learning, every client has to communicate with its neighbors, and there's a huge communication overhead. So as you can see, as decentralization increases, the privacy increases, right? In the sense that the data is stored more and more on clients' personal devices, closer to the client, but then the communication complexity also increases. So our overarching problem statement is how to train GNNs communication efficiently on distributed graphs. However, we focus on fully distributed graphs. Why? Because fully distributed graphs is the worst case. It has the best privacy and the worst communication complexity. So if we can come up with a solution for this, we can extend this to other federated setups as well. So in a fully distributed setup, just to remind you, each client stores only information about one single node and its edges. So if you want to do federated learning, the clients have to share gradients with the server, and there's a common assumption. And we also have two more constraints, and this is specific to graph learning, which is the clients will have to communicate with each other over client-to-client communication channels. And clients will have to share some sort of intermediate representations with their neighbors, and only then the graph learning would be possible. So this is very different from typical federated learning. This is very new. Okay. So to give you a flavor of how GNNs could be trained on fully distributed setup, let's just look at how it might work. So let's say the server sends the GNN to the client, and then the client will have to do a local training step. To do that, it has to do message passing. And in a fully distributed setup, if it has to do message passing, it will have to ask all of its neighbors over the network for intermediate representations. This is a very hard thing to do. And on top of it, you would have to do the gradient computation as well. So training GNNs is basically impractical to do in this kind of a setup, because first of all, you have message passing for every federated learning round. So in every federated learning round, the client has to communicate with its neighbors, and they have to communicate with their neighbors as well, depending on the size of the GNN. So we did a simple simulation, and we found that even to train a 2-layer GNN for end-to-end would require each client to send over 6 to 64 GB of data over the network, depending on what kind of client it is. And gradient computation has to happen over the network as well. This is very different from typical gradient computation, because here the individual clients do not have the full computation graph to compute the gradient. So it has to ask its neighbors for certain factors to compute the gradient. This is a very hard problem by itself. And finally, as it's very common in mobile networks, they could be asynchronous. So if you include that factor as well, then it basically becomes impractical to train GNNs. So we have come down to a place where it's like, I'm just saying it's very impractical, but in this work, we actually give a practical way to train something like GNNs on fully distributed graphs. So we come up with a novel transformation of GNNs called Retexo GNNs that can be efficiently trained on fully distributed graphs with a small performance loss. Because Retexo GNNs require very few message passing rounds. They do not require each one message passing round for every federated learning round. Instead, they just require k message passing rounds if it's a k-layer GNN. And k could be like as small as 2 or 3. And then because of that, it has very low data transfer volume. It could be like an order of magnitude lesser than like training a GNN. And even on client-to-client communication channels, it requires very little data sharing. And also, because of the way it is designed, the gradients need not be computed over the network. You don't need the network to compute the gradients. They can be computed locally, which is very easy to do, and we all know how to do it. And already federated learning platforms implement this. And finally, we show that Retexo GNNs are practical for deployment in mobile networks. And we demonstrate it with the flower framework as well. So to understand Retexo, we need to understand why GNNs require so many message passing rounds. And as I mentioned, every forward pass would require message passing on the network for a GNN to train a GNN. But that's a very high level argument, right? If you think a bit deeper, the reason why we need so many message passing rounds is because of this optimization objective. So the optimization objective for a typical GNN roughly looks like this. So you have to optimize aggregation layer 1 and aggregation layer 2 with respect to the input and output and a loss function. And the thing is, the key observation here is that we have to optimize all the layers simultaneously. Because this is the optimization objective, we have to do this message passing over the network. So this is the key observation. Now let's use this observation to create something different. So our key idea is to use an age-old technique called sequential optimization. It's basically a greedy optimization technique. So what we do is we investigate how to sequentially optimize layers of a GNN based on a local optimization objective. So instead of optimizing all the layers together, we do it one at a time. And we give a novel way to do it for graphs. So it's quite intuitive and simple. So what we do is, so let's say we have a 2-layer GNN. So for a moment, forget that there's an aggregation layer 2. So let's just take aggregation layer 1. And then append a classifying layer on top of it. So now a local optimizer becomes this. What is the optimal aggregation layer 1 that can minimize this loss function? So basically, we try to just pass the features to the aggregation layer 1, and then do classification just based on that, and and then optimize over it. So if we do this, then all A needs to do is just ask features from C, D, and B and store them locally, and then train this aggregation layer. So it doesn't have to do this multiple times. So it just has to do message passing once. So this is just training aggregation layer 1, and this aggregation layer 1 captures information, like it learns how to aggregate information from the 1-hop neighborhood of the graph, forgetting about the 2-hop neighborhood. And then we also need to include information from the 2-hop neighborhood, right? So for that, what we do is once we fix the aggregation layer 1, we pass the features through the aggregation layer 1, get some intermediate representations, which are optimal for the local objective. And then we use that to train the aggregation layer 2. So the optimization function just becomes training aggregation layer 2 based on the conditional inputs that it gets from the trained aggregation layer 1. So in this case, we still need just one message passing round because A just has to ask the intermediate representations from C, D, and B once. And then because it has the aggregation layer 2 locally, it can keep training the aggregation layer 2 locally based on intermediate representations from C, D, and B. So this is the entire idea of sequential optimization of GNNs and Retexo GNNs. So at a high level, Retexo looks like this. So let's say this is a GNN. You can take any GNN. It has 2 aggregation layers. Then apply Retexo on it. It's a framework. So you can take any GNN and apply Retexo on it. So first, it'll create one model which will learn from just the inputs. It doesn't have any aggregation layers. And then it'll use the intermediate representations from the inputs to train another model which stores the first aggregation layer. So the next model will train the first aggregation layer, which will basically find the locally optimal representations from the one-hop neighborhood. And then after that, we'll train another model which will have the second aggregation layer, which will find the locally optimal representations from both one and second hop neighborhoods. So the beauty of splitting GNNs in this way is that to train them in the federated learning setup, it's very easy. So what we have to do is take the first model, the server and the clients together train it, just in a typical federated learning fashion. Now this model could be anything. It could be a CNN as well for all we know. And then you need one round of message passing after it to get representations from your neighbors. And then you train the next model by doing simple federated learning, which also has the first aggregation layer of the GNN. This model will have the information from the one-hop neighborhood. And then you do one more round of message passing to get information from your two-hop neighborhood. And then you do the further training. So you can keep doing this as many times as you want, depending on how many depending on how much information you want from the graph. So this makes it very, very much deployable in practice, even on asynchronous networks, because you can independently do federated learning and message passing. So our evaluation goals are pretty simple. We want to take the node classification task and see how Retexo GNNs perform versus GNNs, because it's a slightly different objective, right? GNNs is global object, like GNNs have a different optimizer and Retexo GNNs have a different optimizer. We want to see how it performs in real world tasks. And then we also want to measure the communication efficiency, Retexo GNNs versus GNNs. And finally, you want to see how feasible it is to deploy Retexo GNNs in federated learning frameworks. So we evaluate Retexo GNNs in semi-supervised node classification task over several data sets using popular GNN models and even using early stopping as well. And these are the results for node classification versus communication efficiency for a few popular data sets. So on the y-axis, you have accuracy, and on the x-axis, you have communication on log scale. And you can see that Retexo reduces the communication by a lot. So it could be even an order of magnitude higher. And the accuracy loss is pretty, like it's very small. It's 2% on average across all settings. And more importantly, Retexo GNNs are actually deployable on typical federated learning frameworks, which means like you can train GNNs on fully distributed graphs. So for this, we use flower to show this. We use flower. So we can't do a fully distributed setup simulation because for that we need a lot of equipment. So instead, what we do is we just take a data set, we split it in half among 2 Raspberry Pis, and then we implement a client-to-client communication channel on top of flower using flower and Blue Dot. It's a different library. And this communication channel is on top of Bluetooth. We choose Bluetooth because we also wanted to simulate asynchronicity in communication. And we have a Flower server, and Flower server code is already there, and the communication between the server and client is pretty simple, and it's already there in the library. So we measure the actual performance of training Retexo simple Retexo GCN. We find that all the performance, like, it can be deployed on small devices as well. So for instance, it just takes 584 MB per client on communication channels, and then client to client communication also, it's just 0.08 MB per message passing around. And in total, it takes about 570 seconds to do the federated learning, with except for we don't include the time when the clients are not in proximity, so they can't share data when they're not in proximity, right? And each client-to-client communication round takes about 63 seconds, but that's only because both of these clients are storing large subgraphs, and they have to share a lot of data. Now, we also assess how it would turn out, how scalable it would be if it was a fully distributed setup. In a fully distributed setup, this would be even more scalable and would require much lesser resources, because there'll be just one node per client, and one node requires much lesser data to train. And the only size requirement is the model size. And also the client-to-client communication would involve very little data to be shared. For instance, if there's in a fully distributed setup, two clients would require only 0.6 seconds to share data between them on client-to-client communication channels, and require much lesser RAM. So in conclusion, we studied this very important problem of federated graph learning, and we show that we argue that GNNs are impractical to train as is in such setups, and we give a novel framework called Retexo, which transforms GNNs into Retexo GNNs, which are practical and efficient to train on distributed graphs. Retexo GNNs can be trained even on mobile and asynchronous environments. And finally, we demonstrate it with integrating it with Flower by extending its code base very minimally, actually. Yeah, that's it. So the code is not public yet, but the paper is. And I can show you the code. We have Dockerized everything, and we have the code ready to be integrated with Flower, but I guess we can talk about it later.
Great. Thank you so much for the talk. It's really cool stuff. I think it's pretty original too. I haven't seen, just like the first talk, both things being talked about today, I hadn't seen much work at all in this space, both on the tooling side and into this on the GNN side. I can take a few questions. One question we received was, let me just look it up. One question, isn't there some leakage of information given the message passing is leaving the client? Doesn't the message encode quite a bit of data?
Yeah, it's a great question, actually. So here we don't look at how much data is being leaked in the gradients or in the message passing, but to train graphs, I mean, of course, there's leakage from the intermediate representations that is being shared between the clients. And I'd say that it's an open problem to how to avoid that, because to train graphs, you have to share something at least with your neighbors about your, to do graph learning, you have to share something with your neighbors, at least some sort of intermediate representations, otherwise it's not possible. And it's a trade-off, like how much you share would directly impact the accuracy as well. And differential privacy could, in some sense, offset it, and I can talk about it perhaps in some other, like offline or in some other presentation, but it's still a pretty much open problem.
I see that's very reasonable. It seems like you're taking one of the first steps to be able to make it trainable in a FL setting, but it seems like initially you've left the kind of privacy aspect of this federation, like most of the early papers.
Yeah, I just want to make sure that it's possible to train.
Yeah, got you. Oh, but one thing, the way that you answered that, it made it sound like perhaps you'd looked into the use of DP in this setting. Is that is that something you have done or in the process of doing?
So one work is something that we have already done, and it's published at CCS. So that is to preserve privacy of the edges from like that are inferred from the outputs of a GNN. Now, for features, there is some work already done, and we're also looking into future works on like how to preserve the privacy of the features. Features.
Okay, I see. Great. I see also Daniel has a question, so I'll let him ask this question directly.
Yeah, thank you very much for the presentation. Yeah, I want to know how Retexo works under a sparse distributed graph. Like, what I mean, if the performance is expected to be good, or it needs to be somehow, let's say, fixed.
Sparse graphs. I mean, we have measured the performance over sparse. Actually, all of the graphs that we've considered are sort of sparse itself. I mean, they don't have too many edges. And in fact, sparse graphs are probably even better for communication because you don't have to like communicate with a lot of neighbors. But node classification accuracy wise, if GNNs work on such graphs, I think Retexo GNNs with a very high chance are going to work on that graph as well.
I see. Good. Well, we're getting a bit low on time and so on, so I think we'll cut the questions off here. But again, thank you for the great talk. It's really interesting to see someone working on this intersection of FL and GNNs, given that GNNs are such an exciting area in of themselves. So let me close things off. Let me just share the final slide, which is the slide we always end on. And that is to say, thank you so much to everyone who's joined us live, and also the people who are undoubtedly going to watch it once it's posted to the YouTube channel. Thank you for attending today. Our next meeting of this Flower Monthly series will be on August 2nd, and that's going to be as usual, the first Wednesday of the month. And we'll keep the time as normal. That's 1600 UTC, and so you could convert that into whatever is your sort of local time, depending where you happen to be. Before we close, I want to remind those people, if you want to like look at past Flower Monthlies, there is the URL there for the prior Flower Monthly recordings. You can also go directly to our YouTube channel to see them. There's also the Slack workspace if you're not currently connected. That's also very useful because there we have a Flower Monthly channel. And so again, this is a community event. And so if you'd like to see us change things up a bit, have some different types of content, just let us know in that channel. And also it's a good channel to kind of follow up anything to do with this particular event itself. And finally, we're currently populating this Flower Events calendar. And if you want to sort of subscribe and sort of see the events pop up whenever we stage them, by all means, please subscribe. There's a nice friendly URL there that you can use to subscribe. And then, of course, the final thing I would say is thank you to our two speakers today. Those are wonderful talks, great content. Lovely to see the work that you're doing in the FL space. It's also a bonus that you have to be doing on Flower. That's great stuff too, naturally. So thank you both for coming today.
Hey, thank you very much. Goodbye.
Yeah, great. Okay, take care, everyone. I'll see you next time.
Bye-bye.